guys, this is going to be the chapter 7.1 note card. So let's go ahead and get started. It says that sampling distributions give insight to true parameters of a population. When we're talking about a population, remember we're talking about everyone. The population includes everyone, depending on what the population is. It could be a population of a high school. It could be the population of the United States. It could be the population of the width of all bottle caps, that kind of thing. Okay, so when we talk about populations, if we're talking about a mean, some sort of mean, okay, or we usually talk about means for quantitative variables. Okay, and then we use the symbol mu, that's the symbol mu. And then for proportions, we use that Greek symbol, which is pronounced rho. I know it looks like a P, but it's actually pronounced rho. Okay, so this is for proportions. Okay, it's usually involving some sort of type of categorical variable. Okay, so that's the major idea. That's in the intro. And it also says sampling distributions are the key to inference when data are produced by random sampling. We'll talk about more what that means as we go through. Okay, so actually getting into 7.1, it says, what is a sampling distribution? That's the title of this section. So first, it defines a parameter and statistic for us. So it says a parameter is a number that describes some characteristic of a population. So we have different parameters. Okay, these are all different parameters, the symbols for different parameters. We generally use Greek letters to represent parameters. So that's like Greek letter mu, rho, lowercase sigma, and then capital N. Some would call that nu. Okay. Then it says before we go off that, all right, parameters always go with some measure of a population. And next it says a statistic is a number that describes some characteristic of a sample. Okay, so populations have parameters, samples have statistics. Okay. And here's some different types of statistics. X bar if we're talking about means, p hat if we're talking about proportions, lowercase s means sample standard deviation, lowercase n refers to sample size. So it says we generally use English lowercase letters to represent statistics. So here's some different measures, just kind of as a review. Mean, standard deviation, proportion, and size. When we refer to sample statistics, a sample mean, we would use the symbol X bar. Okay, sample standard deviation, lowercase s. Sample proportion, p hat. And sample size, lowercase n. Okay, so remember, a sample is just a small subset of the population. But if we had everybody, if we had data from everybody in our population, the population mean would be mu, the population standard deviation would be sigma, population proportion, we would denote that with rho, and population size, capital N. Okay. Now, most of the time, we don't actually know what these things are. Okay, so the next paragraph says, the value of a parameter is usually not known because we cannot examine the entire population. It would take too long, it would be too costly, we would unintentionally leave people out, etc. Okay. It says the value of a statistic can be computed directly from sample data. So kind of like in our penny example, when we took 25 pennies, or 5 pennies, or 30 pennies, what we were doing is we were taking samples. Okay? When we only looked at 30 of them, or 5 of them, or 25 of them. Okay? We can often use a statistic to estimate an unknown parameter. So a lot of times we can't really know what that is because it's not feasible either by cost or time. Okay, so what we can do is we can use an X bar to stand in for mu. Hopefully it's close enough. Okay, hopefully our sample standard deviation can be used as an estimator for sigma. Hopefully our sample proportion can be an estimate for the true proportion or the population proportion. Okay, now I'm not going to draw an arrow here because sample size, we choose that. All right, and it's and little n doesn't stand in for big N. Okay, so let's try this exercise. It says identify the population, the parameter, the sample, and the statistic in each of the following settings. So part A says the Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Okay. Of the respondents, 160 said yes. So let's talk about what each of these things mean for part A. So what the sample is, okay, what is the sample? It's the 515 adults, U.S. adults, that were asked the question. So those 515 people represent a cross-section of all U.S. adults. So what would that make the population? Okay, the population would be all U.S. adults, because sample has to be representative of the population. If our population is all U.S. adults, the only people that we can ask the question are U.S. adults. Okay. So what would the statistic be? Okay. Well, we know how many said yes. 160 out of the 515 said yes. So what that is, that's a proportion. What also clues me into a proportion is I got asked a question and my response can be one of two things. It can either be yes or no. Okay, that's a response. It's some sort of categorical variable. So right away I'm thinking it's got to be some sort of proportion. So our sample proportion, remember statistics go with samples. Our sample proportion, we would call that p hat. And the value of p hat would be 160 over 515. Okay, a p hat always has got to be between 0 and 1 because it's a proportion. Okay, so if we put that in the calculator, we wanted a decimal for that, okay, it would be around 0.31. Okay, so about 31% of the people in the sample believe in ghosts. Okay, that's what the 0.31. You can also write it as a percent, 31%. And lastly, what would the parameter be? Okay, the parameter refers to a population. So our parameter would be rho, and that would represent the true proportion of all U.S. adults who believe in ghosts. Now, we weren't given that in the problem. All right, this was our sample data. Our sample data led us to believe that 31% believe in ghosts. We don't know how close that is to the real rho. Okay, if we did good sampling, hopefully it's fairly close. But we'll get into ways to determine how good our sampling is here. Okay, so that's part A. Part B says, on Tuesday, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contained an average of 19.6 ounces of iced tea. Okay, so let's identify what the sample was. Hopefully you realize that 50 bottles coming off a production line is a relatively small amount. So that probably refers to the sample, okay? Because they picked 50 out of all those, of all the bottles of iced tea. So sample is the 50 bottles of Arizona iced tea that came off the production line on Tuesday. That's what the sample represents. Okay, so what would be the population? The sample has to be representative of the population. So we chose 50. We chose 50 out of what? Out of all bottles. So the population would be all bottles of Arizona iced tea that came off the production line on Tuesday. And the Tuesday part is important because we're testing 50 on Tuesday to represent all the bottles that just came off on Tuesday. Because on Wednesday, they might have some sort of malfunction, all right, and that wouldn't be representative anymore. All right, so what is our statistic? Okay, what information did we get from the sample? This is the information we got from the sample. Okay, our mean, okay, hint, hint, it says average, and this is a numeric or quantitative quantity. Okay, so that's why it clues me in to say that the mean is 19.6 ounces. Okay, that's the mean. Okay, and what's the parameter? Okay, that's the population. What should the average be for all bottles? It tells us that too. It tells us here that the population out of all the bottles, it should average out to be 20 ounces. And since that's a parameter, it comes from the population, I need to use the symbol mu. So that's what it's supposed to be. Fairly close. Okay, fairly close there. So that would represent the true amount of iced tea. Okay, the true amount, or the true mean, I should say true mean, of iced tea in each bottle on Tuesday. That's what it represents. All right. Hopefully you're okay with that. Okay. So let's talk about sampling variability next. It says, take a sample of 50 adults chosen at random and measure their IQ. You could then find their average IQ. This is sample mean X bar 1. So let's just say, on instance, I sampled 50 people. I made them take an IQ test. Okay, and maybe their average IQ of those 50 people was 104. Okay. It says, now take another sample of 50 different adults chosen at random and measure their IQ. Then take their average. Okay, so I'm just going to call that X bar 2, 2 meaning the second sample, this 1 meaning the first sample. Maybe when I do that, the average of those people is 98. It would be very, very unlikely that these would be the same number. Why? Because we're using different people. Even if you use the same people, it's still not likely to be the same. Okay, maybe someone, forgot something the second time around, or they got a little bit smarter the second time they took it. Okay, so not likely to be the same. Okay, so what does this idea or this theory kind of tell us? Okay, it says this basic idea illustrates the idea of sampling variability, that the value of a statistic, okay, like X bar, varies or changes in repeated random sampling. Generally, we use the notion of sampling variability in the following way. It says take a large number of samples from the population. So in this case, say we had the first sample, second sample, third sample. Maybe we took this sample 1,000 different times. Okay, maybe we took 1,000 samples of 50 different people. Okay. And then it says calculate the statistic like we just did for each group of 50. Okay. And then it says make a graph of the distribution of the sample statistics. So if I were to plot all these different sample means on a graph, all right, so for instance 98, 100, 102, 104. And as I start plotting these are all different X bars. Okay. So on our graph, we could make a distribution of sample data. Okay. So we're making a graph, and all those, I know it's kind of hard to see it, they all say X bars. They're different X bars. Okay. Then it says examine this distribution, examine this graph for the shape, the center, and spread, as well as outliers or other unusual features. Okay, so we could estimate what the center was of this distribution. And to me, it looks like the center, the way I drew it, falls about right there. Okay, we could kind of see what the spread or the standard deviation was. If I put it in a calculator, it'd be real easy to figure out the standard deviation of this. Okay, and then we could see if there's one X bar way out here, that might be an outlier. Okay, or other unusual features like gaps or clusters. Right. So what this would be called, as I looked at different samples, that's called the distribution of sample data. Now that's a little bit different when I say something that's called a sampling distribution. Okay, it says the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So let me try to clarify that a little bit, what a sampling distribution is. Okay. So when I talk about a sampling distribution, I'm going to refer back to our penny example. Okay, so in one of our graphs that we've been making over the semester, I tell you to pick 30 pennies, all right, and find the mean year. Okay. In that big tub of pennies I have, there's actually just about 1,000 pennies. So the population size of pennies is 1,000. All right. And my sample size that I'm telling you to take is 30. Now the question is, how many samples are there? Okay, how many different samples are there? If I chose 30 out of 1,000, how many different samples would I get? Okay, well, there's a way we can do this. This is called 100 choose 30. It's a combination problem. Okay, and mathematically, the way we would calculate how many samples there were, we would take 100 factorial over 30 factorial times 100 minus 30, which is 70 factorial. Now this is, it's 1,000 factorial over 30 factorial, 970 factorial. Sorry, I forgot it was 1,000 there, not 100. Okay. All right. There's a quicker way to do this on the calculator. If I go math, and I go over to the probability section, and I choose option 3, which says NCR. Actually, we've got to put 1,000 in first. That means take 1,000 pennies, and I hit that button, the NCR button. I say, okay, choose 30. How many different ways can I do that? It's a huge number. That's like there's 2.43 times 10 to the 57th different samples. Really, really big number. Okay, that's what that E57 means at the end. It's scientific notation because the number's too big to display. All right, now, if I were to plot all the different samples, so X bar 1 all the way up to the very last sample mean, and I graphed it Okay, all these different X bars. Imagine you graphed every single one of those X bars. Okay, just imagine that there's, 200 million, gazillion, billion, whatever that sample is. Then we would get the sampling distribution. This graph would be of the sampling distribution. Obviously, it's not feasible to do that, to get a real sampling distribution. Okay, this is more theoretical than anything else. Okay, that's theoretical. There's no way we're going to take that many different samples. Now, let's talk about what a population distribution is. Because on our sheet here, it says that the population distribution gives the value of the variable for all individuals in the population. Okay. So in a population distribution, again, let's talk about the pennies here that we've been working with. All right, I have 1,000 pennies. If I were to simply take out all 1,000 pennies, I could write down, or I could make a histogram, or I could make a dot plot, or I could make a stem plot, any type of graphical display, up to, I think the last one I had was 2016. All right, and I could just plot out the distribution of those 1,000 pennies. Now, I wouldn't call these things X bars because they're individual values. And so I wouldn't call these things X bars. They're just individual values. And that's the distribution of all 1,000 pennies. So there would be 1,000 dots, okay, if you're doing it on a dot plot. Okay. Or the frequencies should add up to 1,000. So hopefully that makes some sense. So let's keep going on this train here. All right. It says describing sampling distributions. It says a statistic, which is something we get from a sample, used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated. Okay. And we're going to talk a little bit more about what that means. If we take all possible samples of size n, like size 30 in the case of the pennies, from a population, that's the only way we can make a true sampling distribution. What you will notice is that the center of the sampling distribution is exactly equal to the true parameter of the population. Okay, so what does that mean? What does this thing mean? Okay, what does that thing mean? I'll try to illustrate that for a second. This says the mean of the sampling distribution of sample means is equal to the true population mean. All right. So let's say, here's an illustration of why is this true? Why is mu bar of x equal to mu? Why is mu of x bar equal to mu? So what does this refer to? This is the mean of the sampling distribution. Okay. This thing right here is the mean of the population. Why do those two things equal each other? Let's just do an example real quick. Let's say that a population of, I don't know, trying to think of an example here. Population of dollars in my pocket over the course of a week. Okay. So over a school week, we'll just do five values. Okay, so maybe on one day I had $1 left in my pocket. On Tuesday, let's say I had $3 left in my pocket. Then I had $5 left in my pocket, then 7, and then 9. Okay. So if I wanted to figure out what was the mean, so these 5 numbers represent the entire population of a single week, of how much money is left in my pocket. All right, if I took the mean, if I wanted to figure out the mean, I would just add up all the values in my data set. And then since I have 5 of them, I would divide by 5. Okay, so if I add up these 5 numbers, 9 plus 1 is 10, 7 plus 3 is another 10, so I'm at 20 plus 5 is 25. 25 over 5 is 5. So therefore, the mean amount of money for the population is $5. Now let's suppose we took samples of size 2. Okay. And I'll just write it as lowercase n equals 2. So let's figure out how many different samples there would be. Well, I have 5 to choose from. And I hit math, NCR 2. And there's 10 different samples. So there's 10 different samples. Let's see if we can list them. All right, so I'm only picking 2 of these. Okay, so my first sample, let's say I choose the 1 and the 3, of course by random. Then I choose the 1 and 5. Then I choose the 1 and 7. And 1 and 9. Okay. Then let's say I choose the 3 and 5, the 3 and 7, and the 3 and 9. And these are all unique samples. Can't repeat the same numbers twice. You can repeat one of them, but you can't repeat both of the same numbers. All right, so next, we'll see, we have 5 and 7, and 5 and 9, and then 7 and 9. So is this 10 different samples? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So what would this first sample mean be? We would add 1 plus 3, which is 4. And since I have 2 data points, I would divide by 2. So that's 4 over 2, which is 2. All right. X bar 2. I'm not going to go through the full steps. 1 plus 5 is 6, divided by 2 is 3. X bar 3. 1 plus 7 is 8, divided by 2 is 4. Okay. X bar 4, the 4th sample mean. 1 plus 9 is 10, divided by 2 is 5. X bar 5, 3 plus 5 is 8, divided by 2 is 4. X bar 6, 3 plus 7 is 10, divided by 2 is 5. X bar 7, 3 plus 9 is 12, divided by 2 is 6. X bar 8, 5 plus 7 is 12, divided by 2 is 6. X bar 9, 5 plus 9 is 14, and 14 divided by 2 is 7. X bar 10, 7 plus 9 is 16, divided by 2 is 8. All right, so how would we figure out with this thing, mu of x bar, what is the mean? Here's how we would say it. What's the mean of the sample means? Okay, well, here's all my sample means. 2, 3, 4, 5, 4, 5, 6, 6, 7, 8. Okay, and we said there's 10 of them. So if I took these numbers, 2 plus 3 plus 4 plus 5 plus 4 plus 5 plus 6 plus 6 plus 7 plus 8, and divide it by 10, let's see what happens. All right, 2 plus 3 is 5, plus 4 is 9, plus 5 is 14, plus 4 is 18, plus 5 is 23, plus 6 is 29, plus another 6 is 35, plus 7 is 42, plus 8 is 50. So I'd get 50 over 10, which is 5 right here. Okay, so if we looked at all possible samples of size 2, their mean is exactly the same as the mean of the population. All right, 5 equals 5. It wouldn't matter if I picked samples of size 2, 1, 3, 4, or 5 in this case. It wouldn't matter what the sample size was. Okay. If I were to plot all these, that would be a sampling distribution because I have every possible sample of size 2. I have every single sample of size 2. Hopefully that makes some sense. All right. So here's the next statement. And this says mu of p hat equals rho. Okay, this is the mean of the sampling distribution of sample proportions, that's this part, is equal to the true population proportion. So let me try to illustrate this with an example we've been working in class. So as part of our pennies here, I've asked you to take 25 pennies, okay, 25 pennies. I've asked you to figure out how many of the pennies were made on or before 1983, based on the year that's on the penny. All right. So when you guys have been doing this, what you have really been finding, and then after you did that, I said divide it by 25. What you guys have been finding are different p hats. You've been taking samples of 25 pennies again out of the same 1,000 pennies that are in the bucket. Okay. So sometimes when you did that, you found about 15 pennies. All right. Maybe another time you did that, you only got 12 pennies. Okay. On and on and on and on and on. Okay. And you could get, how many different sample proportions could you get? Well, you'd have 1,000, choose 25. That many different, whatever that works out to. Okay. Whatever that works out to. All right, all the way down until your last possible p hat. All right, and then what you have been doing with those values, you would get a decimal. So 15 over 25, for instance, is 60%. Okay, or 0.60, and this one's 0.48. So as you guys have been getting these, all right, you've been plotting. Remember, proportions can't be smaller than 0 or bigger than 1, you've been plotting these p hats based on these values, the decimal version of it. Okay, so you've been plotting some p hats, all these different p hats. And as you've been doing this, or if you repeated this for every possible sample, okay, if you did this for every possible sample that there were, okay, however many gazillion, billion different samples there are, then this would be the sampling distribution of sample proportions. And now this distribution, guys, it has a certain center. If you added up all these different p hats and then divided by how many p hats you had, you would get some sort of mean. Okay, even though it's a proportion, you would get a mean because these are all decimals. You add them all together, divide by how many samples you took, then you would get a mu. So the center would be called mu of p hat. Okay, so that's the mean of the sampling distribution. Okay? And what you would find, okay, or what's true, this has been proven, all right, this has been proven that this center, okay, the center of that distribution is exactly equal to the true proportion. So let's say, for instance, that when you took these, it was 0.53 as an example. The center, you added them all together, and you find out that the mean is 0.53. Well, guess what? Out of these 1,000 pennies, since this has been proven to be true, okay, it also turns out that rho would equal 0.53. Okay? So out of these 1,000 pennies, it turns out that 530 out of the 1,000 of them were made on or before 1983. Okay? So this is true. The mean of the sampling distribution equals the true proportion. And again, this is for categorical data. That's for categorical data. So hopefully that made some sense. Now, the bottom of this sheet says, larger random samples give us more precise estimates than smaller random samples. The variability of a statistic, or the spread in a sampling distribution, is mainly attributed to the size of the repeated random samples with size of lowercase n. It says larger samples give smaller spreads. The spread of the sampling distribution does not depend much on the size of the population, as long as the population size is at least 10 times larger than the sample. The sample size increases, the spread of the sampling distribution shrinks. Much more condensed. Well, what the heck does that mean? Let me try to illustrate that. All right. So how you can see this with our pennies, okay, we did two different graphs for pennies. We made one graph, okay, where I said pick pennies in groups of 30. All right. And another one I said pick pennies in groups of 5. When you look at those graphs, when you take 30 of them, all right, and these are the different X bars that you get, when we graphed that, okay, the values were fairly close. Each one of these represents a different X bar. Okay, let's think about why that's true. Why is this graph so condensed? Okay. Because if I grabbed a penny that was made a long time ago, like back in the 50s or 60s, I have 29 other pennies that pull the mean back towards the center. When I only have 5 pennies, an outlier has a much bigger effect. Okay, so when we looked at samples of size 5, this wasn't quite as condensed. It was further spread out. Okay, so as sample size increases, okay, as your sample size increases, these are both sampling distributions or distributions of sample data. Okay. They're both sampling distributions, but as your sample size gets bigger, okay, the data is much more condensed, so the spread is less. Okay, the spread is less. This has more spread. And so it's an inverse relationship between spread and sample size. As sample size goes up, as there's more people in each sample, the spread gets more condensed, it gets smaller. And vice versa. If sample size is small, your spread's going to be pretty big in terms of a sampling distribution. Now let's finish off this this section of chapter 7. So the next part says bias, variability, and shape. It says we can think of the true value of the population parameter, whether we're talking about means or proportions, as the bullseye on a target, and of the sample statistic, x bar or p hat, as multiple arrows fired at the target. Both bias and variability describe what happens when we take many shots at the target. Bias means that our aim is off and we miss the center. Variability describes the amount of scatter in our shots. It is best to choose a statistic with no or low bias and minimum variability. So when we look at the first one, imagine mu to be right there in the bullseye. Okay. Well, if you notice here, each of these dots represents where an arrow landed. They're all fairly close together, which means that I'm precise. In other words, when I'm firing, okay, there's not much spread. I keep hitting the same place. But the bad part is I'm not very close to where I want to hit. So there's low variability here. There's not much variation in where I'm hitting, okay, but I'm off target, all right? So that's why this refers to high bias, because there's a big distance between where I want to be. Now, in example B here, if you think about all these different points, they are really centered around there, okay? So you're kind of all over the place, but if you were to think about, okay, pulling all those points to some central value, it would be really close to the center of the bullseye, okay? So that's why this one has low bias. Okay, if you were to, in effect, average all of these, think about it like polar coordinates. If you were to average out all these polar coordinates or vectors in a way, they would come pretty close to adding up or summing right to the center. But they're all over the place, okay? They're all over the place. So that's why this is high variability. The dots or the arrows are not condensed. So each arrow represents a certain X bar. You got samples all over the place. Okay? But if we were to add them all up, if we were to add up all those X bars, they would net to about the same as the mean. Okay? So low bias but high variability. That's not a good situation either. C is the worst. Okay, C is the worst out of all these four. Okay, we're not close. If we added up all those vectors, okay, think about each as a vector from the center. If we were to add up all those vectors, we'd be way over here somewhere. Okay, so we're not accurate at all. Okay, so that's why we have high bias. High bias meaning we're off target. Okay, we also have high variability here because our dots are not necessarily that close together, at least not as much as here. Okay, A is better than C because even though we have high bias, okay, at least we're consistent. So here we're off target and we lack consistency. So it's the worst of both. But the best of both is right here. Okay, we're on target with every shot and we're precise. So that would be an example of low bias with low variability. This is the ideal world. Each X bar fairly close to the true mean, okay, which means that there would be a low amount of spread or a low amount of variability. Okay, in terms of a sampling distribution, our X bars are really tight, really condensed. That's the best of both worlds. And then if we were to think about the true mean would fall in the center of all those X bars too. That's why this is the best. All right. And that wraps it up from a logic standpoint and the theory of sampling distributions. Now we're going to use sampling distributions a lot more in the mechanics of some calculations coming up. It's basically the bedrock or the foundation of everything we're going to do in pretty much the rest of this course. So it's important to understand it, understand the theory to do well on the AP exam. Inference is a major factor on your AP exam. So we'll wrap it up there.